Hi, Jemason Further Maths Tutorials. Today we focus on further curve sketching. The question reads, a real valued function f is defined as f of x equals 2e to the x minus 8 all over e to the x minus 2. Roman 1, find the domain of f in the form this, where a is a real constant. Roman 2, evaluate limit as x tends to negative infinity of f of x and the rest of these others, which are simply limits at the boundaries of the domain. Hence, state the equations of the three asymptotes to the curve y equals f of x. Roman 3, find f prime of x and show that y equals f of x has no turning point. Roman 4, obtain a variation table for f. Roman 5, determine the coordinates of the points where the curve y equals f of x crosses the coordinate axis. Roman 6, sketch the graph of y equals f of x. Roman 7, show that the point of symmetry of the curve y equals f of x is line 2, 3. Okay, we start with the first part, which is asking for the domain of the function. So for Roman 1, we have f of x equals 2e to the x minus 8 all over e to the x minus 2. This is a rational function. If it has to be defined appropriately, the denominator should never be 0. When it is 0, the function will be undefined. So we simply get the value of x that makes the denominator 0 and then exclude it from the set of values that the function can take, which now gives us the domain. So I start with e to the x minus 2 equals 0 implies that e to the x equals 2, and so x equals line 2. And that implies that the set of values that this function can take would start from the left of line 2 moving down to negative infinity, or from the right of line 2 moving up to infinity, which we can then say domain of f should be such that there is negative infinity and line 2 as the boundaries of one region, and the two are not included, so we put excluded brackets on them, or which you can also say union again from above line 2 to positive infinity, both not also included, and that gives the answer to the form they want us to express. So our a here is line 2. That was for 2 marks. In Roman 2, we are asked to evaluate the limits at the boundaries. We have the limit as x tends to negative infinity, the limit as x tends to our a, which in this case is line 2, from below and then from above, and then the limit as x tends to positive infinity. So these are simply the limits at the boundaries of the domain which they are asking you to find. And these limits usually provide us with the asymptotes to the curve. It's important to know. Those that tend to infinity provide horizontal asymptotes, and these other ones to the left and to the right of the vertical asymptote confirm that that restricted value of the domain would always be the vertical asymptote. So it's important to know before we arrive there, because we are now asked to state the equations of the three asymptotes to the curve following our results here. So if you miss these limits, you are likely to miss the asymptotes, and of course your curve wouldn't come out as it was supposed to be. Alright, so we start with the limit as x tends to negative infinity. Limit as x tends to negative infinity of the function is simply limit as x tends to negative infinity of that function. I simply plug in negative infinity. I substitute negative infinity in the function and then see what comes out. I have 2e to the negative infinity minus 8 all over e to the negative infinity minus 2. Remember, e to the negative infinity, these cases of limits as x tends to negative infinity have been treated in a video. There is a whole video dedicated to limits at infinity. If you haven't watched it, then look at the video description below this video and you would see the link to that video and you watch it. It is important. So limit as x tends to negative infinity of the function would be this expression simplified. E to the negative infinity is the same as 1 over e to the infinity. E to the infinity is a very large number, so 1 over a very large number gives 0. So this first term should be 0 minus 8 over the same thing here, 0 minus 2, and that gives us 4 as the answer to that limit. Limit as x tends to. They want us to find again this other one. We can start with it. Let's finish with the infinities first. So this other one, positive infinity of f of x, that would be, I plug in again positive infinity, I get 2e to the infinity minus 8 all over e to the infinity minus 2, and that would be, if you evaluate this, you see that this is a very large number, minus 8 will still remain very large, so I have infinity over the same thing, very large minus 2 still remains very large, and that tells you that it is indeterminate. When you're dealing with a rational function and the limit is indeterminate, it's indeterminate simply because infinity over infinity, you can't determine it. There are infinities and there are infinities, which means some infinities could be larger than others. So infinity can be large number, very large number, or even very, very large number. And so dividing an infinity by another infinity is not certain that you can have one, for example, if they are the same, or the one up will be larger infinity than the one down, and so on. So you can't really get an answer here. When that happens, we call it the indeterminate form. You now use L'Hopital's rule. So this could simply be equal to the limit as x tends to infinity of, I differentiate up separately and differentiate down separately, not the quotient rule. You differentiate independently up and down. The differential of up gives me 2e to the x, and the differential of down gives me e to the x. And these two would cancel, and you are just left with limit as x tends to positive infinity of 2. Limit of a constant is always the constant. Then we move to limit as x tends to ln 2 now. This other boundary from below of 2e to the x minus 8 over e to the x minus 2. Now, generally, you should know that the value that is excluded from the domain will always provide the vertical asymptote, as I earlier said. The issue now is when the curve approaches that value of x, it would brush it. It would either tend towards positive infinity or towards negative infinity. And so what we are interested in now is the sign that this infinity sign would take. We already know that as x tends to this value that makes the denominator 0, the curve either tends towards positive infinity or towards negative infinity. So when you are taking that limit, already have in your head that you would have infinity. What you will be interested in now is the sign that that infinity would take. To investigate the sign, I simply take a number, they say from below, so a number to the left of ln 2. Ln 2 is approximately 0.693. So a number to the left of it would be maybe 0.6. So if I substitute or plug in 0.6 in this function, I will get a value, and the sign that that value has would be the same sign that this infinity would take. So if you substitute 0.6 in this function, you would get a positive value, and so this will be positive. You can investigate that with your calculator, you would confirm. So that is the limit as x tends to ln 2 from below. Then the other limit as x tends to ln 2 from above of 2e to the x minus 8 over e to the x minus 2. Again, we know that the answer is infinity, but we are not yet sure of what the sign would be. Again, I go to ln 2, which is 0.693, and take a value slightly above it, since it's from above now, and substitute here. A value above it could be 0.7. So when I substitute 0.7 in this function, I will get a negative value, and so it means that this limit is negative infinity. Now the next part says we should state from these results the three asymptotes to the curve. All right, as I earlier emphasized already, limits as x tend to negative infinity and positive infinity of a function, if they are finite, that means they give values different from positive or negative infinity, those limits become the horizontal asymptotes. So we had 4 for the case of tending to negative infinity and 2 for the case of tending to positive infinity. So we can say hence y equals 2 and y equals 4 are horizontal asymptotes. Then the case of ln 2, we already said that the value of x that is not included in the domain, or values of x, they could be more than 1, they automatically become vertical asymptotes. And to confirm again, as I said, the limit of the graph as x tends to that value, be it from the left or from the right, would always give positive or negative infinity, and it confirms here. So we also say, and x equal ln 2 is a vertical asymptote. Okay, in Roman 3, we are asked to find f prime of x and then show that y equals f of x has no turning point. Roman 3, f prime of x should be equal to, so I have to differentiate f of x to have f prime of x. It's a rational function, so the quotient rule would be used. I start by copying the denominator and differentiating the numerator, which gives e to the x, 2e to the x, minus, I now copy the numerator and I differentiate the denominator, e to the x, all that over, I'll get now the denominator all squared. That is the quotient rule. At the numerator, e to the x is common. I factorize it, and I factorize and then divide the whole of this term by e to the x. I get 2 into that bracket, which I expand to have 2e to the x minus 4. And when I divide this other term by e to the x, I get negative 2e to the x and negative times negative will be plus 8 all over e to the x minus 2 all squared. Finally, I get in the bracket 2e to the x minus 2e to the x disappears. Negative 4 plus 8 becomes 4e to the x all over e to the x minus 2 all squared. That is f prime of x. Now, to have turning points, remember turning points occur on the curve where the gradient is 0, and the gradient is represented by f prime of x. So if I put f prime of x equals 0, I would have it that 4e to the x all over e to the x minus 2 equals 0. And 4e to the x equals 0 has no real solution. And that implies that f of x has no turning point, as the question asks us to show. Now in Roman 4, we are asked to obtain a variation table for f. So to have the variation table, I would start with the x values, which range from negative infinity, and then I must include the vertical asymptote and then positive infinity. There are no turning points, otherwise the x coordinates of the turning points would also appear on that first row for values of x. And so this is the values of x that I need to include on the first row. The next thing is to look at what the curve would be behaving. The sense of variation is actually determined by f prime of x, the gradient. It has to do with whether the function will be increasing or decreasing in which range of values of x. So there are two regions actually, between negative 8 and ln 2, and between ln 2 and positive infinity. And so we need to investigate the sign of the gradient or f prime of x in those regions. The vertical asymptote is here. And then to investigate what sign would appear here, I take a value in this region between negative infinity and ln 2 is 0. If I substitute 0 in f prime of x, substituting 0 in f prime of x, I will have 4 into e to the 0 all over whatever is down there. I will square it. It will not affect the sign of f prime of x. So 4 times 1 over something positive remains positive. So f of x is positive in this region, and that tells us that it will be increasing. When the gradient is positive, the function is increasing. In this other region, I take a value again between ln 2 and positive infinity, any number, 5 for example. If I substitute 5 in f prime of x, whatever is up there would be positive, down is squared will also be positive, and so I will still get positive. And so the graph is still increasing beyond ln 2, which is the vertical asymptote, towards positive infinity. The other region we are interested in f of x, where it would behave. Now as x tends to infinity, we have that the function tends to 4. And so I begin from here. That 4 is a asymptote. The brush down, which is a horizontal, and then begin rise. So it will be increasing towards, we need to see what limit, what was the limit as x was tending to ln 2 from below. When it was tending to ln 2 from below, we had positive infinity. So we write it beside the vertical asymptote. To the right of the vertical asymptote, we had that the curve approaches negative infinity. And so there is negative infinity, and it would be increasing again as indicated by the sign of the gradient. So it will rise. Again, we have, as x tends to infinity, f of x tends to, so it rises to a value of 2 there, which is also another horizontal asymptote. And that gives you the table of variation. Now, the next part says we should determine, the coordinates of the points where the curve y equals f of x crosses the coordinate axis. And so we can say the coordinates of the points where the curve y equals f of x crosses the coordinate axis. And so we can say that is Roman, this was Roman 4, and this now is Roman 5. In Roman 5, we have to find the value of f of x when x equals 0, which would be that y, which is f of x, should be 2e to the 0 minus 8 all over e to the 0 minus 2, which gives, this is 2 minus 8, negative 6 over 1 minus 2, negative 1. So negative 6 over negative 1 should, negative 6 over negative 1 should be 6. And so the point is 0, 6. That's where the graph cuts the y-axis. When y equals 0, which is f of x, 2e to the x minus 8 all over e to the x minus 2 should be 0. That implies that e to the x would be 4. And so x would be ln 4, which is approximately something like 1.4 approximately. We need the value at least to locate on the graph when we are sketching. Okay, that answers Roman 5. We have again the point. The point is 1.4 for x and 0 for y. So that is where the graph cuts the x-axis. And finally, we are asked to sketch the graph of y equals f of x in Roman 6. So Roman 6, I start by drawing this. I can put here 2, 4, 6, and here 1, 2. So the values are based on the points I have, and then some other things like the asymptotes, the vertical and the horizontal. Okay, so we need first to indicate the asymptotes. There is 2. We have y equals 2. So this, there is a horizontal asymptote there. Y equals 2. There is another one at y equals 4. Y equals, and there is a vertical one at x equal ln 2. Ln 2, as I said, should be something like 0.693 approximately. So if this is 0.5, then 0.7, that approximation can give 0.7 somewhere here. would not be too bad, and so I present my vertical asymptote there, which is x equal ln 2. From there now, I need to plot the points. The points are 0, 6, so here the graph would pass here, and there is 1.4. This is 1.5 should be here, 1.4 should be here. The graph would pass here. For me now to sketch this graph, after getting all these points and the asymptotes in place, I go back to the table of variation. It will help a lot. Now remember, we have to start from 4, which is a horizontal asymptote in the boundary between negative infinity and ln 2, the vertical asymptote. So in this region, we start from the horizontal asymptote, which is 4. So the graph would brush it and then begin to increase, rise, positive gradient, pass through that intercept, which was 0, 6, and then approach the vertical asymptote. So that is the graph in this region between negative infinity and the vertical asymptote. On the right of the vertical asymptote, graph starts from negative infinity and rises until it would brush this 2, which is a horizontal asymptote. So from here the graph would be rising. Again, the gradient is positive in that region, so it will be rising and passing through the intercept, which is 1.40, and then approaching the horizontal asymptote. And that gives you the curve. In the last part, Roman 7, we are asked to show that the point of symmetry of the curve y equals f of x is ln 2, 3 for 2 marks. So usually the point of symmetry on a curve like this one would be the intersection of the asymptotes. So on a graph like this, we can get the point of symmetry simply by manipulating the asymptotes. If there is one vertical asymptote, like in this case, that is already the x-coordinate of that point of symmetry. If there are 2 of them, then you take their average, because the point of symmetry would lie at their midpoint or midway between them. Now, if there is only one horizontal asymptote, it gives directly the y-coordinate of the point of symmetry. And if there are 2, again, it will be midway, the y-coordinate will be midway between them, or simply their average. So here, point of symmetry occurs where x equals the vertical asymptote, which is ln 2. If there were 2 vertical asymptotes, add and divide by 2, because it will lie midway between them. So take note. So we just have 1, so it gives ln 2. And y equals, if there was only one horizontal asymptote, that is already the y-coordinate. Since there are 2 of them, the y-coordinate is their average, because the point lies midway between those 2 horizontal asymptotes. So the y would be 2 plus 4 all over 2, which gives 3. Therefore, point of symmetry is the x, which is ln 2, and the y, which is 3, as required. Generally, if AB is a point of symmetry on the curve y equals f of x, Then if we prove that f of a plus x plus f of a minus x equals 2b, if we are able to show that this left hand side is equal to the right hand side, we would have shown. So if you care, you can try that by using this formula instead to see whether you would get that the substitution of maybe a in this case now is ln 2, f of ln 2 plus x plus f of ln 2 minus x would give you 2 into the y coordinate, which is 3, which is 6. So if you are able to show this, you can try it at your leisure time. It will give 6. So this is the condition you can always use in some situations. If the question were asked without the graph, show that this is a point of symmetry on the curve f of x equals this, then you would have to pass through this to arrive there. It's quite lengthy, so given the number of marks too that were given for the question, just 2 marks, we needed to just do this argument using asymptotes to arrive the point of symmetry.